Tagadan 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 pam pam tagadan 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 pam pam tagadan 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 pam pam tagadan tagadan pam pam tagadan.
Next is Gil Bloch from the UCF Consortium to talk about Open Smart Network Application Programmable Interface, also known as OpenSNAPI. Gil, welcome.
Thank you. Thank you. Let me just share my presentation and I'll start. Thank you. Thank you, Brian. So yes, I'm representing the UCF. It's great to be here. I'm going to talk about, let me just have my laser pointer and be able to switch slides. Yes, so I'm going to give you a quick introduction to UCF and some of the projects, and then mostly focus on the OpenSNAPI. And I'll go back to UCC, which I'll present shortly at first as a use case for OpenSNAPI. And I think if you've followed Gilad's presentation, it will make my life easier because I'm not going to have to convince you that DPUs or programmable network devices are important. I'll just show you what we are doing as a community to ease the use of those devices. Before we start, I want to thank the organizers. This is a picture I took in Lugano in 2019. Unfortunately, last year was canceled. This year is online. Hussein, I really hope that next year I'll have a new picture and meet everyone. It always has been a pleasure to be in this conference. That includes this year. But still, I miss the opportunity to drink coffee with everyone and have a chat. So I'll drink my coffee now and you can ask questions and I'll answer that at the end of the presentation. Unfortunately, no coffee break and chat after this presentation, which is too bad, but that's what we have for this year. So let's start. UCF, Gilad already mentioned UCF. UCF is an organization with a mission to build collaboration between industry, laboratories, academia, and all that collaboration is to create production-grade communication frameworks and not less important, open standards for data-centric ML, machine learning, and artificial intelligence, and high-performance computing applications. This mission, while it's a long sentence, to make it short, I'd say there are two important words here. One is collaboration, and the other is open. We want to work together with everyone that is that cares about using high-performance computing infrastructure, building scalable, high-performance infrastructure for HPC, AI, big data, or any other application. There are multiple projects and working groups that are that are working under the UCF consortium. I'll mention some of them with some more details, but here you have the list. That's UCX. I'll talk about what UCX is. Hopefully most of you are already familiar with UCX. There is the Spark UCX, OpenSNAPI, which I'll give more details today. UCC, UCD, HPCA. I'm not going to go through all the details. I really encourage you to go to the UCF Consortium webpage. You'll have access to the presentation, so you will have the link. I want you to go there, see what it is that we're doing, and join us. We are looking for everyone who can give feedback or collaborate with us to build better environment and enable the use of HPC and AI and all the infrastructure. You can see the list of board members. I'm not going to go through all the names, but I guess you at least know Gilad Shiner. And we had DK Panda giving the keynote yesterday, so some of those names you're familiar with. You can see that there are, again, academia like Ohio State University, industry like NVIDIA and AMD and IBM, national labs like Los Alamos and Aragon. And again, we want you to join, and I'll remind you that later and why. Let's start with some of the projects we've been doing in the past almost decade. I'd say the first one is UCX. UCX basically is a point-to-point communication library, as simple as that, with the mission of enabling data movement on any infrastructure. Any CPU architecture, x86, ARM, Power, or whatever it is that you would like to use, CPUs and GPUs. It's not a vendor-specific kind of infrastructure. It works with NVIDIA or AMD GPUs. It should work with DPU memory, right? Gilad already presented those new animals, new devices, network devices, and I'll talk about DPUs in just a few minutes. And it is being used not just by the trivial MPI, it's being used for many other use cases like storage, data analytics, machine learning, in many different use cases, which makes UCX a very interesting framework because it enables integration of the best of all the different use cases, so that if you go and build your storage infrastructure and you don't have to write everything from scratch, you actually got all the optimizations, the low latency, high bandwidth, and efficient optimizations someone else did for MPI. And it's true the other way as well. If you do MPI, you can benefit from all the nice features that storage added, like compression, security, and other features that are more common in storage infrastructure than in MPI. And you can now get that for free just because it's a part of a single pipe that enables you to move data. UCX is a very interesting project that is basically started with multiple vendors having their own solutions. Like PAMI from IBM, MXM from Mellanox, what used to be Mellanox and is now NVIDIA, and other solutions, and all the experience, all the learnings, all the code came into a group that decided that it makes more sense to work together on a single open solution than having multiple proprietary solutions coming from different vendors. I think the collaboration between the vendors, bringing decades of experience, made UCX a real success. It's a huge success. We see UCX being deployed in so many different use cases. And I'd say this is an example of how to make collaboration to build an open source solutions. So that is for UCX. UCC is another project under the UCF consortium, and it's driving, again, taking the same thing we had for point-to-point, where multiple vendors had their own proprietary solution, bringing all those vendors and labs and academia, all the experience of more than 2 decades of developing collective communication, bringing everyone to the table to work together and collaborate on an open source solution, which is not just for a specific application. It's not just MPI collectives. It's collective that can be used for MPI, for OpenSHMEM and other PGAS libraries. It can be used for AI, distributed machine learning. It is being used for IO workloads that requires collective communication. So again, widening the spread of this solution, bringing all the expertise from the different companies and different groups, to build an open source solution. I'll get back to UCC later today, but I wanted to get to where we actually, the topic that I wanted to cover, and that is OpenSNAPI. OpenSNAPI stands for Open Smart Network Application Programmable Interface. I hope that the name gives most of the details that you need to understand. It's open. It's for smart network devices, and I'll talk about smart network devices, and it gives you the APIs. So there was a question to Gilad about standardization. I'd say what we try to do is to build standards for how to use DPUs, how to use network devices. And I'll get to some more details, and not just build the standard, but also provide an SDK or libraries, again, open source, that will help you build whatever it is that you want to build. So let's start with the mission for OpenSNAPI. So it all starts with the data-centric computing architecture, and Gilad talked about the new paradigm of using CPUs and GPUs and DPUs or IPUs, there are multiple names, to create the next generation data center. And when we talk about IPUs here or DPUs, I'd like to extend a bit the definition. Gilad talked about DPUs, which are a smart network adapter. An IPU basically is a smart network device. From my point of view, I don't care if the smartness goes into a network adapter or a switch. You could have multiple options for smart network devices. And before I go to the next part of the mission, let's talk about what does it mean to have a smart network device. So smart network device is not a device that can offload some smart functionality. That's not enough. In this term, when we talk about smart network devices, we talk about programmability. Being able not just to do smart things, but to do programmable smart things. To be able to do A and B today, but to do A, B, C, and D tomorrow because someone thought of a new idea, programmed that, and enabled new functionality. These are the smart devices that we're going to talk about. Gilad talked about DPUs, and he showed the example of a specific product, a specific DPU that integrates a network adapter with offload functionality and smart things, but doesn't make it a smart device. But it's an SoC that integrates both the network adapter and ARM programmable cores. Now it's a programmable smart network adapter, or a DPU. When we look at that, we want to, again, look at, this is one use case, but we want to look at many other use cases at the OpenSNAPI community. An example would be, again, the SoC integration. That's one example, but it can be a network adapter and an FPGA. I don't know if it still exists, but Mellanox had such a product that had a board with a network adapter and FPGA, or just a highly programmable network adapter that have, I don't know, P4 or other interface for programmability and allow you to program the pipeline. And now you can add functionality to that. And we want this programmable functionality to enable services to both local and remote processes. Local meaning a process that runs on the same host that includes the DPU, for example. Remote might be if you want to offload or provide a service from a switch to multiple nodes. So it's remote. You need to send information through the network to get to the switch. And with that, let's go back to the mission that I wanted to talk about. So the mission is to create an application programming interface for accessing those, here it says compute cores, and that's aligned for the DPU case, but it can be to any programmable logic. And specifically for the network adapter, I'll later talk about an example of an offload engine and functionality we already built for smart network adapters. And again, the idea is to allow you to get access to those new cores and run whatever it is that you want to run them. And we can talk about so many use cases. and so many ideas on what can be done with a smart network device, or in this case with a DPU. So Gilad showed the case of communication library Offload. Actually, DK Panda presented yesterday how they offloaded all-to-all collective operation into a DPU, and showed the great benefit of having overlap, and the great benefit that eventually accelerates FFT, for example. That's one example. Another use case could be just running an application offload. Take a part of your application that you could easily separate from the entire application, put it on the blue field or the other DPU that you have, and let it run there. You can, these two are actually require a lot of synchronization between the host, the user, and the service. But there are other use cases like data analytics and profiling, for example. You can just put something that follows whatever is happening in the host, the communication, and many other things on the DPU, and either do that for profiling to show where the bottlenecks are, or do that for anomaly detection and figure out if someone is trying to do something that it shouldn't. You can do remote execution. I'll skip that. Gilad already mentioned active messages. And you can do security in two different ways. One of them is a security offload. Let's say that I want to encrypt all the data that I'm sending to the network. So the process can ask an offload engine to encrypt the data. And it can also be a security enforcement, meaning it's not something that the user actually wants to happen. It's something that the infrastructure would like to install, so that when the user is trying to do things, this security enforcement logic that runs on the DPU will make sure that the user is actually allowed to do that. Again, as a part of the cloud native supercomputing, now you have logic that sits between the user that runs on the host and the network, and actually isolate the user from the entire infrastructure to make sure that even if the user somehow compromises its own operating system and its own host, it still is limited to the boundary of the host. This is, again, another example. And maybe the more important thing is that these are all ideas that I've already heard from different people. The most interesting part is that you can add your ideas, and it should be as easy as possible to take an idea and make it reality. And I'd say this is one of the parts that we at OpenSNAPI community are trying to do. We're trying to figure out, okay, what it is that you need, that everyone will need, to try and build another service, another offload engine, another acceleration engine. There are building blocks that, if we provide you, will make your life much easier. And this is actually what we're trying to do in OpenSNAPI. There is no very specific definition, like we need to support send and receive. No, what we're trying to figure out is how can we make it faster and easier to take a smart network device and implement a new logic, your logic, not our logic. And here you can see some of the things we have already mapped and started working on. The first question that we have asked is, okay, so I have a new logic. I've implemented some code that does some offload. How does it get to the smart NIC? Or how does it get to the smart switch device? How do I get my new service into the DPU? And there are multiple options and different use cases, and there is no one good answer to this kind of question. If it's a security enforcement kind of feature, we don't really want the user to install it, right? Because the user can later uninstall it. We probably want it to come from the factory, or at least be a software update that the user doesn't have access to. Only the infrastructure, only the admin can install new software. On the other hand, in some cases, the user might have, let's say, MPI collective offload. In this case, you want the user to be able to upload the latest and greatest version of this offload, and then it can be either when the job starts running or at runtime. You can think about it as a logic, just like what you do with the GPU kernels, right? You compile your code with the GPU code. You co-compile everything into one binary, you run it, and there is some magic that takes the code that needs to run on the GPU, takes it and runs it on the GPU. Could I do the same with a DPU? There is no reason why not, right? Except for, again, if the DPU is in a secure mode and it isolates between the user and the network, you might not want to allow the user to run its own code because then the DPU might be hacked as well. So again, there is no one good answer, and probably we will need to enable more than one way to provision your service into the smart network device. Once provisioned and running on the smart network device, we need some way to register the service and discover the service. Because, okay, how do I know what kind of services do I have on my local GPU? How do I know if there are other services away, not on my local DPU, on one of the switches? I'm not going to go and discover all the switches, and I need a general way to discover all the services on the network so I can use the services that I believe will be best for my own applications. Once we discover, we need to create some communication channel. I need to be able to communicate with the service. I need to be able to configure the service. I need to be able to send data to the service or get data from the service. And these are all questions that we're already started working on. Some of them are already sort of solved, or at least at some level. Some of them are still at the discussion stage. And I want to talk about one example, and that is the communication channel. What we did, I'll shortly show what we already did and what exists today. And again, show you the questions that we are asking ourselves, so that you understand what it is that we are trying to solve. And if we miss questions, this is where we want you to be able to give us feedback, join us, and help us answer the right questions. So for the communication channel, we want to create a secure communication channel for control and data. It might be the same communication channel, but in some cases, since control, you don't care too much about performance, can be one channel, and data, you might want a different channel, maybe with less capabilities, but much higher performance, or less flexibility, but higher performance. So there are multiple options here. And there are basic assumptions that are very important for us. The first one is you might not have network address of the service. The service might run on the local DPU, and there are cases, sorry, there are cases where you have no access, no SSH, for example, to the local DPU. And the reason is, again, if it's a cloud-native supercomputing architecture, and you want to make sure that whatever is running on the DPU is secure and belong to the infrastructure, and the user has no access to it, you cannot let him SSH into it. That's a great example for the case where there is no TCP access, there is no socket, no SSH to the DPU. But again, I want to be able to communicate with a service that was provisioned there, let's say, by the infrastructure, by my admin. So this is where we started. And this is just to show what it is that we're trying to do. We're trying to build these APIs that will enable applications running in virtual machines. This is just an example. Having multiple virtual machines with multiple applications and multiple services running on a SmartNIC. And now what you'd like to do is to create connectivity between specific applications and specific services. And you might say that I want this service to be able to serve applications from a specific VM, but I don't want to give this service to another VM. Why? Because it didn't pay enough, or because it's a specific service that was built by a specific user, and he doesn't want any other user to be able to access that. So there are multiple security and isolation terms that needs to be solved. And on the other hand, I want to allow multiple applications from multiple VMs to access a specific service. And I want each application to be able to access multiple services. So it's a many-to-many mapping with security requirements that we've been working on. We've built, again, I don't want to go into the details too much, but what we're trying to build here, these are APIs for sending and receiving messages and connecting, and I won't get into the infrastructure of how we did that. What I did want to show here is that we started with the most basic functionality possible. Send, receive, connect, listen, that's it. And the reason we started there, sorry. The reason we started with such a basic functionality is to make sure that even if what you have is an FPGA and not programmable ARM cores, you still want to implement support for that. We want to make sure that the standard APIs, sorry, we want to make sure that the standard APIs will work on any smart device, not just on a DPU or a specific DPU from a specific vendor. It needs to work on everything. And we want to make sure that later your program and services can run on any infrastructure. So we started with that, and to that we added some more support for zero copy put and get, for example. And the idea is to build it as a modular APIs so that you can say, okay, if it's an FPGA, it only supports that. If it's next level of, let's say, ARM-based DPU, it will support put and get. And there is a way to query the support so you can build your application to use the best available channel out of whatever is supported by the DPU. But there is always some minimum functionality that must be supported by all devices. So you know that it will work on each device, but it might get better performance on devices that have more sophisticated functionality. Let me skip that, and I just want to go back to the collective offload for just a few minutes. I hope I'm not too late. I'll do that as quick as possible. What we did is to take, we talked about UCC, right? The framework and working group that does collective communication. And now we want to see how we build collective communication offload engine as a part of this open source community. Again, it's a part of the UCF consortium. And I'm not going to get into too many details, but the nice thing is that we ended up with an architecture that takes your, let's say, MPI application that runs on top of UCC. And what we did is split UCC to be UCC client running on the host and a UCC server that runs on the DPU. And the idea is that the UCC client is a very shim layer that takes the command from the MPI application. And what it does is to forward it into the DPU. And the nice thing is that in order to forward from the client to the server, it's using OpenSNAPI. This is the communication channel we just talked about. And then this UCC server, if it wants to communicate with other UCC processes running on different DPUs, it can actually use UCX, again, a UCF project. So we end up building an infrastructure that takes the different components and use those building blocks to build a very sophisticated collective offload engine on top of, again, OpenSNAPI. I'll skip this logic, and with that, I want to thank you for listening and following this presentation. And feel free to ask questions. And oops, I'm missing one slide, so I'll go back to this slide. And again, I really urge you to look at what we're doing at UCF. Go to the website, join us, join the community, give us your feedback, participate in the working groups. I think it's a great opportunity to build a community and collaboration to build open solutions.
Great, thank you, Gil.
Bum 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 bum